This video is going to be talking about what's called the ideal gas law. The word ideal refers to perfect conditions. So there are the five postulates of the kinetic molecular theory, and if a gas behaves properly, they should abide by all of those postulates. Well, if they do that, then we would call it an ideal gas. Well, of course, in the real world, that doesn't always happen. Sometimes there's attraction forces between gas molecules. Sometimes the volume changes, pressure changes, things change. So that would be considered a real gas. But what if, in a perfect world, they act ideally? Well, they came up with an equation, and that equation is PV equals nRT. That is the ideal gas law equation. Pressure is measured in atmospheres, volume is measured in liters, N stands for the quantity or the number, which is the moles. R is the constant, and then K is Kelvin. Temperature is Kelvin. R in this situation, so we've been dealing as proportionality with the variable K. I'm now changing that specifically for the ideal gas law, and we're changing it to R. So the R is the combined proportionality constants of all of those other laws put together, kind of wrapped up in one, called the universal gas constant. So I'm going to show you how to find the universal gas constant, and then we'll go through an example equation. So just really quickly, based on experimental measurements, when gases behave ideally, there's a very specific set of conditions that take place. You have 1 mole of that gas. It is at 1 atmosphere of pressure. It takes up a volume of 22.4 liters and a temperature of 273 Kelvin. So if all of those conditions line up, then the gas will behave ideally. So this condition is called standard temperature pressure. So they've given it an abbreviation, or STP. So we can know the variables at STP. We know that these are the variables at STP. So I can just say in an equation, at STP calculates this variable, knowing that these are what STP equals. Okay, so I'm going to show you how to calculate the R constant. Okay, so I'm going to show you how to calculate that R to figure out what that value is. So we have these variables. So I'm just going to move this paper over. So I want to calculate R, so PV equals nRT. I want to get R alone so I can solve for R, so I'm going to divide both sides by what's attached to R. So these are all being multiplied, so that multiplication carries down, and then divide out both sides. So my moles and my temperature cancel out on the right. So my equation, if I rewrite it, R equals PV divided by N multiplied by T. So R equals those ideal conditions. 1 atmosphere of pressure, volume 22.4 liters. I most ideally am going to have 1 mole of the gas, and the temperature is going to be at 273 Kelvin. So when you multiply across and divide by the denominators, you're going to get an R equal to 0.082. Here's the tricky part. None of these units are the same. Therefore, they all go in the answer. So the units on R are ATMs multiplied by liters divided by moles times Kelvin. That is the universal gas constant given ideal STP conditions. Okay, so now that we have R, we can calculate any one of these other variables using PV equals nRT. So here's my sample equation. So please make sure you write this down. So a sample of hydrogen gas, which is diatomic, it exists in pairs, has a volume of 8.56 liters at a temperature of 0 degrees Celsius and a pressure of 1.5 atms. Calculate the number of moles. So that's my unknown right there. So if my number of moles is my unknown, I'm going to write the base equation, PV equals nRT. Well, I want to solve for n, so I'm going to divide both sides by what's attached to n so I can get the proper equation. N equals PV divided by RT. So this is the equation that I want to use to solve for N. So another thing I noticed is that my temperature is in the wrong units. So if you remember from the last video, Kelvin equals degrees Celsius plus 273. So because it's 0 degrees Celsius, Kelvin equals 273. So that's the number. So that's an ideal condition, so that's great. All right, so now let's plug in some values. So my pressure is 1.5 atm, so this is out of ideal conditions, but that's okay. My volume is 8.56 liters. We can still figure out how many moles are in this, regardless of ideal or unideal. Inimeal, I don't know. And then my R is that value that I just calculated, 0.082, and I have to write all of those units. Yes, it matters. And then my temperature is 273 Kelvin. Okay, so the reason why I'm writing all the units is to show you what units are left over. What units are left over? So I have an ATM in the numerator, ATM denominator. Liters numerator, liters denominator. This Kelvin is in the denominator of the denominator. So this denominator will cancel out with this numerator. And the only units I have left are moles. So that unit carries down into my answer, which makes sense because I'm solving for N. And so to calculate this, 1.5 times 8.56 divided by 0.082 divided by 273. 0.57 moles.